Howdy gang, welcome back. Congratulations on surviving your second exam. It's nice to see you all here. Today we're going to be moving out of polynomial land. So if you've just had it up to here and beyond with polynomials, rational functions, and all the bullshit we do and build with them, take a deep breath, because today, I promise, no polynomials. The flip side of that coin is, of course, we are going to be doing something else. And that something else is talking about what are called exponential functions, which is a whole new family of functions for us, totally different from anything we've seen before. But there will be some features of functions we had seen before showing up here, of course. These are still functions, so we're going to be looking at graphs and stuff like that. But I think you'll enjoy it. I think you'll find it as a kind of neat new thing for us to play with. And a lot of people find exponential functions in some ways much more satisfying and pleasant to work with than polynomials. I know I certainly do. But yeah, let's go ahead and turn on the screen share. We can start to do the thing. So this, of course, is MAC 1140, section 009, which is a pre-calculus class. And today is the 28th of October, 2021. But today, as promised, we're going to begin talking about exponential functions. And this sort of third unit of the class, if you want to call it that, is by far the shortest. So I want to warn you that exam 3 is coming. It's coming much faster than you may think. The gap between exam 2 and exam 3 is a lot shorter than the gap between exam 1 and exam 2. So yeah, that's just that. There's only like 4 sections, right? We talk about exponential functions, 4.1 today. Next time, we're going to talk about the natural exponential function and the number e, and then start talking about logarithms. That's 4.2 and 4.3. And then 4.4, we're going to be talking about properties of logarithms, and then exponential and logarithm equations and how to solve them. And that's it. Then it's time for the test. So just be aware, try to stay on top of things. Don't let yourself fall behind in the homework. Keep up with the lectures, and you'll find this to be a very pleasant kind of middle part of the class. After that, we're going to start talking about some pretty out there shit. We're going to talk about systems of equations and then very quickly abstract them into matrices. We'll talk about matrix algebra, which is an amazing, beautiful thing. It's the introduction to a whole new world of mathematics called linear algebra. But for today, exponential functions. Little announcement. The tests, exam 2. Will be graded within a week. My goal is always to get them graded within a week of when you take the test. Now, unfortunately, we have a lot of people taking the test at the testing center, a lot of people taking the test at alternate days and times, and of course, some people taking the test online here in normal class time. So it's a little bit tougher for me to get everything organized and back to you as quickly as I would if this were an in-person class, but I'm gonna do my best to get this stuff back to you within 1 week. If you missed exam 2 for whatever reason, if you haven't taken exam 2, for any reason, please come to office hours this Friday, where I'll be doing the makeup. Right, so just a reminder, if you did miss the test, there is a makeup test. It's going to be this Friday in office hours. That's tomorrow, right? Today's Thursday, Wednesday, Thursday, right? Yeah, so that's tomorrow. Come for that makeup test if you haven't taken it. It's the last opportunity to take the test, barring some exigent circumstances. That's the deal with where we are, where we're going, what we're doing. let's get into it. Just for fun, the way I like to introduce exponential functions with a kind of a silly story. How many of you have read the book Of Mice and Men? They used to make people read this book in high school. It's a novel by John Steinbeck. Just give me a thumbs up, react, or whatever in Zoom if you have. Anybody? A little less common these days than it used to be. Soraya, cool, I'm glad to hear it. So Steinbeck is one of my favorite authors. Really love Steinbeck. If you enjoyed Of Mice and Men, I implore you to check out Garden of, I don't know, what is it? It's been so long. East of Eden. East of Eden. Definitely my favorite Steinbeck book. Really, really good. It's an amazing author. It talks about the Dust Bowl in America and kind of the migration west where a bunch of people moved out towards California. This was before labor unions. It was before any sort of labor laws. So workers were treated very badly. And it's a fascinating story about the American spirit. Which is something that's easy to be super cynical about, right? I think there's a lot that we can say negatively about American culture, especially over the last 5 or so years. But Steinbeck, to me, kind of does a really good job of capturing something that is beautiful about America. And I think it's a nice time to remind ourselves of that it's not all trash. Not to say there aren't plenty of problems. Anyway, that's neither here nor there. The example I like to use to introduce exponential functions involves the characters from Of Mice and Men, George and Lenny. You may recall that Lenny really wanted some rabbits. George and Lenny, their goal was to get a farm, and Lenny, big guy, dumb guy, really big, strong guy, but not super smart, wanted some rabbits. So here we go. Assuming the book ends better for them than it did, George and Lenny buy a farm. On day 0, Lenny finds a rabbit. The next day, George gives Lenny a rabbit. Gives Lenny another rabbit and warns him that every day after that, the number of rabbits will double. Rabbits being rabbits. Of course, this is a mild exaggeration. I don't think rabbit populations ever double every day. But I'm changing the numbers from the real world to make it a little bit nicer mathematically. So on day 0, Lenny's got 1 rabbit. The next day, George gives Lenny 1 more rabbit. So on day 1, Lenny has 2 rabbits. And every day after that, the number of rabbits is going to double. Rabbits like to make more rabbits. We want to find a function f of x, which gives the number of rabbits on day x. And I think the best way to go about this, if you don't have any previous experience with exponential functions, is to start by making a little table. So over here, we'll put x. Over here, we will put f of x. X is the day, and f of x is the number of rabbits in Lenny's hutch. On day 0, Lenny found a rabbit, right? So on day 0, Lenny gets 1 rabbit. The next day, on day 1, George gives Lenny another rabbit. So on day 1, Lenny has 2 rabbits. And then every day after that, Let's go down to 4. The number of rabbits will double. So how many rabbits does Lenny have on the second day? On day 2.
4.
Good. All right. Every day the number of rabbits doubles. He had 2 the day before, so the double of that is 4. Okay. On day 3, how many rabbits does Lenny have?
8.
8, right? Because every day the number of rabbits doubles. These rabbits are busy. And on day 4, how many rabbits?
16.
Very good, 16. Okay. Now remember, our goal is to say how many rabbits there will be on day X. And before we make a conjecture there, I want to make a few observations about these numbers in the right-hand column. What do you notice about these numbers? 1, 2, 4, 8, 16. Maybe look at these guys first, just 2, 4, 8, and 16. Think about their arithmetic properties. If you had to describe these numbers to somebody, what would you describe them as?
Are all multiples of 2?
Definitely, they're all multiples of 2, right? They're all even numbers. That's what that would mean. More is true though, right? So between 4 and 8, there's another multiple of 2, 6. Between 8 and 16, there's several, 10, 12, and 14 that are not listed. So what's special about these particular multiples of 2?
It's a power of 2.
Yes, perfect. Not only are they multiples of 2, they are pure powers of 2. They have no other multiples in there. So 6 is divisible by 2 and 3. 10 is divisible by 2 and 5. These are all numbers which are divisible only by 2. In other words, they're powers of 2. 2 is 2 to the 1. 4 is 2 to the 2. 8 is 2 to the 3. And 16 is 2 to the 4. And it happens to be the case, conveniently, that 1 is 2 to the 0. So now compare the orange to the left column. When x is 0, we have 2 to the 0. When x is 1, we have 2 to the 1. When x is 2, we have 2 to the 2. When x is 3, we have 2 to the 3. When x is 4, we have 2 to the 4. So in general, what do we expect to see down here? F of x, the number of rabbits on the xth day, if we follow this pattern, would be what?
2 to the x, power of x.
Yeah, 2 to the power of x. And that's it. That's the answer to the question. Right? F of x, the number of rabbits that these guys will have on the xth day, is 2 to the x. And before we go much further, I want to talk a lot about this function today, but before we go much further, I think it would be nice to sketch a graph. We've already done, all the work here making this table. We might as well go ahead and draw the graph of this function. This is a totally new function. This is not any sort of polynomial or rational function. It's not any sort of root or power function. This is a function of a type we have not seen before. And its graph looks a little bit different than any of the graphs we've seen so far this semester, although it does have some features that we will recognize.
This is exponential function.
It is, yeah, this is an exponential function. My outputs go as high as 16, so let me come up here and call this 16. Halfway to that would be 8. Halfway to that would be 4. Halfway to that would be 2. Halfway to that would be 1. I'm not going to label the 1. And then let me put some x values in here. We're going from 0 to 4 so far, so we'll call this 1, 2, 3, and 4. So I've got this table. Let's plot the points. 0, 1, that's right here. 1, 2 is right here. 2, 4 is right here. 3, 8, which is up here, and 4 comma 16 is way up here. And while it doesn't have anything to do with rabbits, we can extend this function to negative values. I can plug in -1 and -2, for example. If I plug -1 in here, f of -1 is 2 to the -1, or 1/2. F of -2 would be 2 to the -2, which is 1/4. So if I want to, I can extend over here to -1 and -2. On this scale, right, if this guy right here is at height 1, then height 1/2 is like this, like almost touching the x-axis. And 1/4 is so small, we really can't even see it. It's like right down there. If you could zoom in just on this piece of the graph, you would see there's a gap between this point and the x-axis, but it's a small gap. And this, I think, is enough to get a feel for what's going on with the thing. So let's go ahead and draw it. We'll come through here like this. And we're getting very steep as we go over here further and further. And as we come out this way, the graph is sitting down really hard on that x-axis. It's hard to draw. But something like this would be what our graph looks like. As you go further and further to the left, as you put in bigger and bigger negative numbers, these fractions, the next one with -3, you'd have 2 to the -3, or 1/8. And remember, 1 over a big number is a very small number. Where have we seen that before? Well, when we talked about asymptotes. So this guy does have a horizontal asymptote. It's the line y = 0. Okay. So here's my graph. And I want to point out a handful of things about this graph. First, let's talk about the obvious stuff, the domain and the range. So this arrow here kind of indicates that the graph goes forever and ever in this direction, just getting closer and closer and closer to that horizontal asymptote. And this arrow over here indicates that the graph goes forever and ever and ever in this direction, just getting taller and taller and taller. So what is my domain?
All real numbers.
Domain is all real numbers, from -infinity to infinity. And what about my range?
0 to infinity?
Very good. So as we go further and further to the left over here, we get closer and closer and closer to 0, but we never hit it. So the lower end of my range is a parentheses 0. And as we go further and further to the right over here, this graph is exploding. It is getting so tall, definitely going as tall as you want, up to 0, from 0 up to infinity. And while I haven't defined what an exponential function is for you yet, I just want to make a note here that these are the same for any exponential function. Using the definition of exponential function that our textbook has. Let me go ahead and define that for you then. So since we're making this claim that these are the same for any exponential function, let me tell you what it is we're going to consider as exponential functions in this class. This is an example of one, right? And kind of what makes this different from all the other functions we've seen in the past. In the past, we've seen things like x to the 2 or x to the 3, stuff like that, where the base is a variable and the power is a constant. Here, those roles are reversed. So an exponential function, let's say a function of the form f of x equals a to the x is called an exponential function. So when I say that this domain and range is the same for any exponential function, I mean functions like this, some constant to the x. The number a is called the base. And we require that a is bigger than 0 to avoid imaginary numbers. You'll see in a minute, I can do things like plug in x equals 1/2, right? This graph right here is continuous. So there is a point here where x is equal to 1/2. If I tried to use a negative number for a and then plug in 1/2, you'd be taking a square root of a negative, which would give you an imaginary number. We want to avoid that stuff. We want these functions to have real inputs and real outputs. Okay. Looking back at this graph for a second, I claim that George and Lenny are in some real trouble. If you wanted to find the next point on this graph, you would have to double this height, which would send you up to the top of the page. So after 5 days, they would have 32 rabbits. After 6 days, they would have 64 rabbits. After 10 days, they would have something like 2,048 rabbits. George and Lenny are very quickly going to drown in rabbits. In other words, this function 2 to the x is a very fast growing function. Right? You may have heard that you can only fold a piece of paper in half so many times, right? Like I don't know what it is, 5, 7, some number of times. And if you were to fold a piece of paper in half something like 20 times, that paper would then be as thick as the distance from the Earth to the moon or some crazy bullshit like that. It's because of how fast these functions grow. So even if you start with a very small number, like we started with 1 here, if you double that number every day or every time x goes up by 1, you will very quickly get a large number out. I'd like to show you the graph of 2 to the x in Desmos. And let me write down what I'm saying first here, and then I'll show you the graph. So it is a fact that exponential functions like 2 to the x, they grow much, much faster than polynomial functions. Like, for example, x squared. So what I mean when I say that, now let me show you the graphs in a larger scale, Desmos, where we can zoom in, zoom out, all that good stuff. What I mean by that, and here's 2 to the x, looking very much like we drew it, right? You see over here, it's growing quite quickly. And over here, it's settling down on 0. As we go further and further to the left, like here's the point 1, 1, negative 1, 1/2, thereabouts. Negative 2, 1/4. This would be negative 4, 1/16. And as you go further and further to the left, these numbers, these y values are getting very, very, very small, very, very close to 0. So that is this horizontal asymptote. Desmos is telling you it's actually 0 here. It's not. That's a rounding error. If you zoom in, you'll see that there is still a gap between this curve and way in. There is still a gap between this curve and the x-axis. Still getting that rounding error. but it's there. Maybe we're close enough now. Yeah, see? So as we come out further and further to the left, this thing is sitting down on the x-axis really hard. And as we come over here and go off to the right, you'll see that this thing is going like straight up. Now, of course, it's not literally going straight up. It wouldn't be a function if it did. That would fail the vertical line test. But it's very, very steep. Right? So this is what I mean when I say that exponential functions grow quickly. That as you go off to the right here, this graph gets incredibly steep and it explodes, it blows up really, really fast. And sort of a natural thing to compare it to is this guy, which we've played with a lot. So when you stay close to 0, they look kind of similar over here, right? They appear to be growing at a similar speed. But if you zoom out a bit, you'll see that the blue grows much, much, much faster. Look how steep this is compared to this. If I zoom in here, the blue is practically vertical. It's going like straight up. And the green it's growing, but it's not growing anywhere near as fast. And if you pick any particular x value, like say I want to compare these things at x equals, I don't know, 9 or 10 or something like that. F of 9, 512. Call this, instead of y, I'm going to call this g of x. G of 9, the output from x squared at that same value is 81. And as you go further and further, that difference gets bigger and bigger. That's, well, 20 versus 20 squared, which is 400, right? You see, this is so much bigger than this. So the blue curve, 2 to the x, grows much faster than x squared. It's honestly not even close. If this were a race, this is like a top fuel dragster. This is like a granny pushing a grocery cart. Not even close. We can get quite quantitative about that. Besides looking at the graphs and convincing ourselves. And to that end, I'd like to ask you, what object that we've studied in the past, think back to chapter 2, has to do with the speed at which a function is growing? Think about like slopes, right? Yeah, average rate of change, right? The rate of change. So if I want to be quantitative about this, we can, by this I mean, that the rate of change for 2 to the x is much bigger than for x squared. And I'll pick some particular x values and do a comparison here in a minute. And I'm saying rate of change rather than average rate of change, because there is also a thing called an instantaneous rate of change. And that's an object you're going to study in calculus called a derivative. For us, the only one we can really play with, because we don't have calculus yet, is the average rate of change. So let's compute a couple of average rates of change. The average rate of change for 2 to the x, and let's look, say, from x equals 8 to x equals 9, what would this be? Well, remember, it's f of b minus f of a divided by b minus a. So that would be 2 to the 9 minus 2 to the 8 divided by 9 minus 8. I'm looking at a step size of 1 here. So the downstairs, 9 minus 8 is just 1. 2 to the 9 is 512. And 2 to the 8 is 256. If you do any work with computer programming, you'll memorize your powers of 2 pretty quickly. 512 minus 256 is 256. So this is 256 divided by 1, or just 256. that same average rate of change for x squared, so the average rate of change for x squared from x equals 8 to x equals 9 is 9 squared minus 8 squared over 9 minus 8, which is 81 minus 64 over 1. 84 minus 64 would be 20. So this is 3 less than 20 is 17. So sort of the slope, or how steep the x squared graph is from 8 to 9, is 17. And if I gave you a line with slope 17, you'd probably be like, yeah, that's a pretty steep line. But then if I compared that to a line with slope 256, you'd be like, whoa, okay, this is a lot faster growing than this. So that's what I mean when I say top fuel dragster granny with a grocery cart. Really not even close. 2 to the x grows so much faster than x squared. And there's nothing special about the 2's here, right? 2 to the x grows faster than x cubed, x to the 4, x to the 5. Pick your favorite polynomial function here. I don't care. X to the 1000 minus x to the 100 plus 25, whatever. 2 to the x will trump it big time. Not even close. 2 to the x destroys any polynomial function. And so do other growing exponentials. You have 3 to the x or 1.15 to the x. All of those will grow much faster than any polynomial. It might take a little bit for this guy to beat this guy. All right, it might take a little bit for this guy to be bigger than this guy, but it will happen eventually. And once it happens, this guy will leave any polynomial function in the dust. So exponential functions, they might sometimes take a little while to get going, but once they go like straight up. Whereas polynomial functions, they grow, and some of them grow quite quickly, but none of them grow as fast as even the slowest growing exponential. So George and Lenny are in trouble. They're going to drown in rabbits. In fact, it would take less than a year for the whole Earth to be covered in rabbits in that scheme. So it's a slightly unrealistic scheme, but you know, it's fun. Okay. Based on their name, you can imply that exponential functions have a lot to do with exponents, right? Obviously, the big thing here is that the variable is in the exponent, right? The variable is the power. So before, your base was the power, and your base was the variable, and you had some constant powers. And we studied all sorts of things like that. Now, your variable is in the exponent, and your base is a constant. One of the consequences of this is that you need to be comfortable with the rules for exponents, and that's why we call them exponential functions, because the variable is in the exponent. So if you're going to start plugging weird numbers into these, like 1/2 or -3/4, you kind of need to know how to deal with weird powers. So before we go any further, I just want to remind you the fundamental rules for exponents. This is something I'm sure you've seen before, but we need to have them handy. I need to be comfortable with these. So just the algebra rules. Burn these into your brain and never ever forget them. The first few are super intuitive. For example, if you take a number a and raise it to the b, and then you multiply that same number a raised to the c, what do we get? Well, a to the b is a times a times a times a, b times. So what you get when you multiply a by itself, b times. And a to the c is a times a times a times a, c times. So this whole thing together is a bunch of copies of a. How many? We've got b copies of a here, and you're multiplying that by c copies of a here. So altogether you have b plus c copies of a. So a to the b times a to the c is a to the b plus c. There's a similar rule for division. if you're dividing like bases, you have something like a to the b divided by a to the c. You can think of this numerator as a times a times a, b times. So you've got b copies of a all multiplied upstairs. And the denominator is a times a times a, c times. So you've got c copies of a downstairs. So you can cancel a bunch of a's from the top to the bottom. And what will be left over upstairs is some number of copies of a, but not all b of them. You'd have b minus c of them. So a to the b divided by a to the c is the same as a to the b minus c. The last rule that kind of fits this pattern, if you take a to the b and you raise that whole thing to the power c, this is c copies of b copies of a. In other words, not too much light coming through the window, sorry. So the inside here is a times a times a times a, b times, right? It's a multiplied by itself, b times. And then I want to take that whole thing and multiply it by itself, c times. So this whole expression is b copies of a copied down c times. So that's a to the b times a to the b times a to the b, all c times. That's a to the b times c. These are the fundamental rules for exponents, and you can actually deduce all the properties of exponential functions from these. However, there are some others that are useful. Negative exponents show up quite a bit. If you want to take a number a and raise it to the negative b power, this is the same as taking the reciprocal of a to the b. So a negative power flips you over. And because 1 to the b is the same as 1, this is all the same as 1 over a to the b. Right? If you multiply 1 over a times 1 over a times 1 over a, b times, the numerator is 1 times 1 times 1 times b times, and the denominator is a times a times a times a, b times, and that's going to be 1, because 1 times itself a bunch of times is still 1, and the denominator is a times itself a bunch of times, b times to be specific. So these three things are all equal to each other. The next rule has to do with fractional powers, so exponents, which are themselves fractions. And usually here we think of the fraction as being made up of whole numbers. So I'm going to use, instead of b and c, m and n. All these rules work great for any real number, b or c. This last rule, though, you usually see it where these two numbers in the power are whole numbers. This is the same thing as the nth root of a, all raised to the m, or the nth root of a to the n. So the downstairs here tells you what root you're taking, square root, cube root, fourth root, fifth root. And the numerator here tells you what power you raise a to before you do that. And because of rule 3, and the fact that b times c is the same as c times b, this is the same thing as the nth root of a, all raised to the m. So you can kind of do those in whatever order you want. If you want to raise a to the m and then take the nth root, you can. Or if you want to take the nth root of a and then raise that to the m, you can do that too. Sometimes one is easier than the other if you're just doing a computation. There are some other things here that I would like to share with you and make sure you're comfy with. First, if you take a and you raise it to the 0, you're going to get 1. Any number raised to the 0 is 1. along with this, I'll say a to the 1 is always a, and 0 to the b is always 0. The only exceptions here, a is not allowed to be 0. 0 to the 0, it turns out, is undefined in the same sort of way that 0 over 0 is. And for precisely that same reason here, I'm assuming that the power b is not 0. 0 to the 0 is undefined. There's two more things I want to share with you here that I wouldn't really count in the same league as these. They're algebra facts that you should know. I'll say also, if you have a ratio like a over b, and you want to raise that whole thing to the c, this is a over b times itself, c times. So this is the same as a to the c over b to the c, because fractions multiply straight across. And if you have a product of two numbers raised to some power, that's ab times ab times ab, c times. Because multiplication is commutative, you can shift it around so that all the a's are next to each other and all the b's are next to each other. This is the same as a to the c times b to the c. And these really are all the rules for exponents that you're going to need to get through this course and your calculus course. And you will need all of them. We need to be comfy with all of them. So put these somewhere in your notes that you won't lose them. From time to time, I'll refer back to them. You can think of 4 as being a partial consequence of this first bottom thing. All right, really what I'm doing is taking the power b and giving it to the top and bottom separately here to go from here to here. And then this is the definition of the negative first power together with the b power. So if you were to take c here to be -1, you would get this. They interact with each other. Okay. With that in mind, I'd like to work another example. Just evaluating. I'm going to give you an exponential function, and we're going to find some values. And then we'll draw some more graphs. So let's evaluate the function 3 to the x, f of x equals 3 to the x, at x equals 5, -2/3, the square root of 2, and pi. Some are more manageable than others. In fact, these get worse as you go on that list. So 5 is probably the easiest to make sense of, -2/3, a little weirder. Root 2 and pi are frankly a bit strange, but we'll get there. It's not that bad. Let's start with f of 5. Since f of x is 3 to the x, f of 5 is 3 to the 5. And there's nothing wrong with writing it like this, but in this particular case, we can find a nicer way to express that. 3 cubed is 27, 3 to the 4 is 81, so 3 to the 5 is 3 times 81 is 243. To figure out f of -2/3, we need to start the same way we started here. So f of anything is 3 to that thing. So f of -2/3 is 3 raised to the -2/3 power. And from here, we're going to use our rules for exponents. So what would be a good first step in trying to simplify this number? Trying to understand, for example, how big this number is.
Use step 5.
Yeah, let's see through here 5. What did we say 5 was? Yeah, we're definitely going to use 5. I think before that, there's even something a little simpler we can do. Remember, a to the negative b is 1 over a to the positive b. So this would be 1 over 3 to the positive 2/3. And now I can use step 5 to clean up 3 to the 2/3. So according to rule 5, I should say, 3 to the 2/3, which is downstairs here, is the cube root of 3 squared. So we're going to square 3 and then take the cube root of that. And 3 squared is 9, so this is 1 over the cube root of 9. And I'll be honest, I don't know what the cube root of 9 is. I have no idea. But I can start to make some sense of how big it could be, right? And I'd like you to think along with me on this. So give me without a calculator, a ballpark for how big the cube root of 9 might be and a reason why. I know this isn't obvious. 9 isn't a perfect cube, right? If 9 was a perfect cube, then I could tell you exactly what this is. Are there any nearby numbers to 9 which are perfect cubes?
8.
Yeah, 8's a perfect cube, right? 8 is 2 cubed, 2 times 2 times 2. So 9 being a little bigger than 8 should have a cube root a little bigger than 2. Let me make a little note here. The cube root of 9 should be pretty close to the cube root of 8, which is 2, just a bit bigger. Right? 9's pretty close to 8. The cube root of 8 is exactly 2. So the cube root of 9 should be something a tiny bit bigger than 2. So about how big should this whole fraction be?
Like around 1/2.
A little smaller than 1/2. I like what you're thinking there, but I want to be just make a tiny adjustment. So if this denominator is a little bigger than 2, then this fraction 1 over that is going to be a little bit smaller than 1/2, right? Like 1/3 is smaller than 1/2. So if this denominator is a tiny bit bigger than 2, then this whole thing should be a tiny bit smaller than 1 over 2 or 1/2. Now, if we want to be more quantitative, we certainly can, and calculators are useful here. There are some problems in this homework where you're going to need a calculator. The TI-30 can do everything that you guys need to do here. If you don't have a TI-30, I don't really care what you use in the homework, but make sure that you're understanding what's going on. So first, let's see, what is the cube root of 9? So 9 raised to the 1/3 power. Yeah, just a little bit bigger than 2, right? That's what we thought. So his reciprocal, which is the thing we're after, is a little bit smaller than 1/2, right? 0.5 would be 1/2. So what does this come out to? 0.4807. I'll just say that's about 0.48. Good enough for us. I do want to point out that this is an irrational number. Anytime you're taking a square root, cube root, whatever, of a number that isn't a perfect square, cube, whatever, that number will be irrational. So the cube root of 9, guaranteed irrational, because 9 is not a perfect cube. And this is not a terribly hard fact to prove, but it's not something that we're doing in this class. So the full decimal expansion for this number would go on and on and on forever because it is necessarily irrational because 9 is not a perfect cube. But this is a good estimate, right? Really, really close to 1/2. which is what we would have gotten from this. Okay. Moving forwards, f of the square root of 2. Now things have gotten weird. The square root of 2 on its own is an irrational number. So I can't say this is like some root of some power of 3. Right, this is 3 raised to the power of square root of 2. And since I cannot write the square root of 2 as a fraction, m over n, that's what it means to say the square root of 2 is irrational. It can't be written that way. There's no way to play this sort of game with it. Now, I do know that root 2 is about 1.4. So I know this should be about 3 raised to the 1.4 power, but fuck if I know what that is, right? 1.4 raised to 2. It's going to be bigger than 3 to the 1 and smaller than 3 to the 2. So bigger than 3, smaller than 9. 1.4 is a little closer to 1 than it is to 2, so maybe a little bit closer to 3 than it is to 9, but that's as good as I can say without using some tools. So if I want to know what is this, I take 3 and I raise it to the power of square root 2. And indeed, 4.7, a little closer to 3 than to 9, between 3 to the 1 and 3 to the 2. Rounding there, that would be 4.73. And then finally, f of pi. Well, this is by definition 3 to the pi. And I can apply that same sort of reasoning I used for the square root of 2 to estimate the size of this. I know that pi is 3.1415926, blah, blah, blah. So 3 raised to the pi should be a bit bigger than 3 raised to the 3. Pi is a tiny bit bigger than 3. So 3 to the pi is probably a tiny bit bigger than 3 to the 3. 3 to the 3, or 3 cubed, is 27. So I expect this to be a little bigger than 27. But how much bigger? 5 bigger? 2 bigger? It's not immediately obvious, but we can ask. And we say 31.54. So yeah, a little bigger than 27. Those sort of estimates that we were doing there, super useful, right? You want to be in a place where you can think your way through to about how big is this number without calculating it. Now, of course, you will have your calculators, and if you want to do the calculations, you always can. But the more you can build that intuition, the easier you'll understand exponential functions. And you notice that most of these outputs are irrational. Most of these outputs are weird numbers. And exponential functions belong to a family of functions that spit out weird irrational numbers. All right, all of these weird irrational numbers. Exponential functions are sometimes are called, or they are a part of a family of functions called transcendental functions. And just a quick react in Zoom. How many of you are taking a trigonometry class right now? Anybody taking trig at the moment?
I do.
Okay. Yeah, commonly taken together. If not together, I'm sure many of you will take trig recently, or yeah, as Susanna said, took it last year. All of your trig functions are also transcendental functions. Let me show you something in the calculus book here. So here's the book we're using to teach calc right now at Santa Fe, also the same book we use at UF. You'll notice it says on the cover here, early transcendentals. What that means is they introduce transcendental functions early on. Things like exponential functions, sines, cosines, logarithms, You can define them the way we do here, using geometry for the trig or using algebra for the exponentials, but they can also be defined in terms of calculus operations. And some textbooks, especially old-fashioned kind of classic, highly rigorous textbooks, prefer to wait until after you have a bunch of calculus to introduce those functions and then use calculus definitions for them. We do not, right? We say early transcendentals, meaning we're going to start messing with those functions early on. The reason they're called transcendental functions is because these are functions which spit out transcendental numbers. Has anybody heard of a transcendental number? So the word transcendental is a weird word. What it means, it's based on the word transcend, which means to like go beyond, right? You talk about transcendental meditation, right? To meditate, to kind of go beyond this world, some bullshit like that. No offense to any transcendental meditation fans. A transcendental number is a particular kind of irrational number. So I promise here's the only mention of polynomials, which are irrational numbers that are not the root of any polynomial with integer coefficients. So we've talked about irrational and rational numbers in the past. An irrational number is just a number that can't be written as a fraction using whole numbers. And you can think of those as also being numbers whose decimal representation goes on and on and on forever without ever repeating or having a pattern. The irrational numbers themselves can be split up into what are called transcendental irrationals or algebraic irrationals. An algebraic irrational is an irrational number that is the square or is the root of some polynomial with integer coefficients. Think of the square root of 2. The square root of 2 is irrational, but it's also the root of the polynomial x squared minus 2. And many irrational numbers show up like that. However, numbers like pi are transcendental. It's an irrational number, and it's also not the root of any polynomial with an integer coefficient. Other transcendental numbers include e, which we're going to start talking about next class. Many outputs from logarithms. The sine of 1 is, I believe, a transcendental irrational. And there's a lot of open questions in mathematics where you take a constant that is known to be irrational and ask, is it transcendental? And it's a big field of number theory, which is the branch of math in which I do my work. Okay, so exponentials are transcendental functions. Transcendental functions are very special for a number of reasons. They often can be defined through calculus operations, which means they're nice with respect to calculus operations usually. Also, they spit out these special numbers called transcendental numbers, and 3 to the root 2, transcendental. 3 to the pi, definitely transcendental. 3 to the negative 2/3, this is an algebraic irrational, but I won't prove that for you here. And exponentials are transcendental functions. Okay. Calculating these outputs often requires use of these rules for exponents, and you want to get comfy with those rules for exponents. And later, when we're solving equations involving these exponential functions, you'll be needing those all the damn time. The next thing I'd like to do is to sketch a couple of graphs for you. I want to graph this function, 3 to the x, and a closely related function, 1/3 to the x, and see if we can't notice some similarities and differences between them. And also use them as models to classify broader families of exponential functions. We're going to do this the old-fashioned way by plotting points. And then we'll use this to introduce the idea of transforming these graphs using the rules from section 2.7 or 2.6. But first, by plotting points. So that means I'm going to make a table. First, in purple here, I'm going to make a table for F. And I'll use as my inputs some nice numbers, -2, -1, 0, 1, and 2. F of -2 is 3 to the -2. And how do I find 3 to the -2?
One divided by 3 to the power of 2.
Perfect. So this is the same as, according to our rules for exponents, 1 divided by 3 to the 2. And 3 to the 2 is 9. So this is 1 divided by 9, or 1/9. We want to work with fractions wherever we can. F of -1 would be 3 to the -1. And that is 1 over 3 to the 1, or just 1/3. F of 0 would be 3 to the 0. And since anything to the 0 is 1, this is also 1. F of 1 is 3 to the 1, or just 3. And F of 2 is 3 squared, or 9. And you may notice some symmetry as we go up and down this list. 1/9, 1/3, 1, 3, 9, kind of neat. And if I graph this function by plotting these points, one, 2, -1, -2. We'll call this up here 9. That's the largest output I have. A third of the way up to him would be 3. And a third of the way up to him would be 1. And I will not label the 1/3 and 1/9 because there just isn't room. But over here, when x is -2, I have the point -2, 1/9. That's teeny tiny, that y value, way the fuck down here. That would be 1/9 of the way from here to here, which is like, whoa, way down there. We also have the point -1, 1/3. So that x value is right here. That y value would be 1/3 of the way up to there. So this one we can actually see, but still very, very small. Next, we have 0, 1, which is right here. And then 1, 3, which is right here. And then 2, 9, which is right here. If I wanted to go over one further step here to x equals 3, that would be 3, 27, which is well above the top of the page. So this is about as much as I can hope to fit here. And we can just connect these dots with a nice smooth curve. And he's going almost straight up here. And he's going almost straight over here. Down. And we have this horizontal asymptote. Y equals 0, right? The next entry as we go further negative, when x is -3, that would be 1 over 27, which is almost indistinguishable from 0 at this scale. So this graph is sitting down really hard on the x-axis over here, and it's blowing almost straight up over here. And this is the graph, y equals f of x. I'm going to use a different color for the next guy. So next we're going to graph g of x, which is 1/3 to the x. Same business, plotting points. And I'll use the same inputs, -2, -1, 0, 1, and 2. Remember, g of x is 1/3 to the x. So g of -2 would be 1/3 to the -2. Which is the reciprocal of 1/3 to the 2. In other words, that's 3 squared, or 9. G of -1 would be 1/3 to the -1, or the reciprocal of 1/3 to the +1. That's just 3 to the 1, or 3. One-third to the 0 is 1, because anything to the 0 is 1. 1/3 to the 1 is 1/3. And 1/3 to the 2 is 1/3 times 1/3 is 1/9. And now on a similar size axis here, I'm going to attempt to draw the graph of G. Okay, we'll call this 1 and 2 and -1 and -2. We'll call this 9, which makes this 3, which makes this 1. On the graph of G, the orange graph, I'll have -2, 9, which is up here. I'll have -1, 3 right here. 0, 1 right here. 1, 1/3, which is round about here. And 2, 1/9, which again is already so small, it almost looks like it's sitting right on the x-axis. And if I connect these with a nice smooth curve, just following that pattern, I get something looking like this. And the question I would like to ask you guys is, do you see a relationship between the orange graph?
The symmetrical
Yeah, what is the symmetry?
y-axis.
Good. If I flip, and let me draw my asymptote here also, right? If we're drawing our graphs, we should be good about this. We have a horizontal asymptote here. It's also the line y equals 0. Yeah, if I flip the purple graph over the y-axis, it becomes the orange graph. Or conversely, if I flip the orange graph over the y-axis, it becomes the purple graph. These appear to be it appears to be the case that F and G are horizontal reflections of each other. Does anybody remember the way to describe using algebra two functions which are horizontal reflections of each other? Like if I want to take my parent graph and flip it over the y-axis, well, what's the formula for that? Think back to your transformation stuff, right? 2.7, 2.6, sorry. Okay, that's all right. So i.e., it appears that g of x should be the same as
f of minus x.
Yeah, very good, right? When we multiply on the inside of the function by a -1, that flips everything over horizontally. Can we verify this algebraically? Well, let's see. Indeed, f of -x, that would be 3 to the -x, which is 3 to the -1 all to the x, right? That's the rule a to the b all to the c is the same as a to the b times c. And that is 1/3 to the x, which is g of x. So yes, they are. These are horizontal reflections. And you could go the other way. You could show that g of -x is the same as f of x. Same sort of procedure. I invite you to try that. Okay. I would like to take one more second, if I can, to sketch a graph as a transformation of another graph, right? So to start with one of our new parent functions, all of these basic exponentials like a to the x are now in your family of parent functions. So 2 to the x, 5 to the x, 3 to the x, 10 to the x, 1/3 to the x, 1/5 to the x. These are all a part of our new family of parent functions. I might not have time to do that just yet. So let me just share with you a little bit of terminology, and I'll trust that you guys can manage your way through the transformation work. You may need to look back at your 2.6 homework to do this. If I tell you to take a walk along this graph, the purple graph going from left to right, you're a little dude here and you're going to go for a walk. Is this going to be an easy walk or a hard walk?
Hard.
Yeah, this is right. Anybody who's been hiking in the mountains knows this is going to be exhausting. This function is always increasing. You would always be going uphill. And we call that exponential growth, or a growing exponential. And any exponential function where the base is bigger than 1 will have a graph that looks like that. So 3 to the x, 5 to the x, 2 to the x, 10 to the x, pi to the x, 1.27 to the x. All of those will have a graph that looks like this. The exact points will be a little bit different, but it will have this shape and this asymptote approached on the left, and it will go up on the right. And we call those growing exponentials. And again, the key to figuring out which one of these two shapes your graph will have is to look at the base. If the base is bigger than 1, your graph looks like this. On the other hand, if I strap some skis to your feet and send you down this guy from left to right, you're going to be hauling some pretty serious ass by the time you get over here. This is always decreasing. And we call this exponential decay. And this means that your base A is smaller than 1. So if you're trying to graph any exponential function where the base is less than 1, like 1/2 to the x or 1/3 to the x, or 0.12345 to the x, it will look like this. It will have roughly this shape. In particular, it will be decreasing. You will be going up on the left, and you will be approaching this horizontal asymptote, y = 0, on the right. I know that we are out of time here, and unfortunately, I do have a 2 o'clock meeting today, so I will get to the transformation stuff. We'll talk a little bit more about that together on Tuesday of next week, but I am expecting you to be able to do it. We've done lots of graphing with transformations in the past, and you use these 2 basic graph shapes as your parent functions. Anything like 2 to the x, 3 to the x, 4 to the x, 5.7 to the x will look like this. And anything like 1/2 to the x, 1/3 to the x, 0.57 to the x will look like this. And you can transform these, shift them up, shift them right, flip them over, all of that stuff to get graphs of more complicated exponentials. You have a homework set open right now that has you practicing this, and I want you working on that. It is due next Tuesday. Next Tuesday, we're going to talk about the number e, which is a special number that we like to use as the base of exponentials when we can. And then we will start talking about logarithms. So by the end of next week, we will have talked about inverses to exponentials. We'll finish all of our exponential stuff, and we'll be moving into properties of logarithms. Following that, we will talk about logarithmic and exponential equations, and then we'll be having exam 3. So again, exam 3, much sooner than it may feel. Please stay on top of the homework. If you have trouble with any of this stuff, I do have an office hour tomorrow from 1 to 2 p.m. And as always, you can reach out through Canvas or Discord or wherever. But that's it from me for today, guys. I hope you found this fun, informative, all that good stuff, and I will see you all next week.